Our universe began in a state of pure, searing chaos. For a fleeting moment after the Big Bang, not even atoms could exist, only a frenzied sea of raw energy. This is the story of how that primordial fire transformed into everything we see, from glittering galaxies to the planets that orbit them. By the end, you will understand the night sky as a dynamic history book, with each star telling a chapter of an ancient struggle between disorder and structure. How did microscopic quantum whispers become the blueprints for galaxies? What cosmic alchemy forged the very atoms in your body from nothing but energy? The answers trace our existence back to the first split second of time. What does it mean to know we are built from the ashes of that first chaotic fire? This first cosmic chapter was written in a language of pure energy. For a fleeting sliver of time, the entire observable universe was compressed into a space smaller than a single atom, a realm of such staggering density and heat that the familiar rules of physics simply did not apply. In this furnace, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, unified power. There was no matter as we know it, only a seething, opaque ocean of energy so intense that particles could not maintain their identity. This was the quark-gluon plasma, a primordial soup, where the most basic building blocks of reality, quarks and gluons, zipped about in a frenzied, constant dance of creation and annihilation. They would briefly snap together, only to be instantly torn apart again by the overwhelming energy of their surroundings. In this state, not even a single proton, the heart of every atom, could form and survive. It was a cosmos of maximum chaos and minimal structure, a state physicists call maximum entropy. Imagine the most uniform, featureless substance you can conceive, a perfectly smooth, endless expanse of shimmering fog with not a single ripple or variation. That was our infant universe. It was the ultimate blank canvas, a masterpiece of pure, undifferentiated potential. Yet this very smoothness presents the central mystery of our existence. If everything began in such perfect, homogeneous disorder, where did the fingerprints of structure come from? How could a cosmos so uniform ever produce the magnificent clumps and clusters we see today? The answer lies in the most microscopic of whispers hidden within that apparent perfection, quantum seeds sown in the first unimaginable moment. Hidden within that perfectly smooth primordial fog were imperfections on a scale we can barely comprehend. If you could shrink down to the quantum realm in that first fraction of a second, you would have found the universe buzzing with a faint, statistical static. These were quantum fluctuations, temporary bubbles of slightly higher or lower energy that flickered in and out of existence according to the fundamental uncertainty woven into the fabric of reality. On their own, they were utterly insignificant, microscopic whispers lost in the roar of the cosmic fire. But then, something extraordinary happened to give those whispers a cosmic megaphone. The universe underwent a transformation so violent and rapid it defies all everyday intuition, a period known as cosmic inflation. Think of a perfectly smooth balloon, its surface dotted with the tiniest, almost invisible specks of dust. Now imagine that balloon inflating at an incomprehensible speed, doubling in size not once, but dozens upon dozens of times in less than a blink of an eye. Those microscopic specks are stretched along with the rubber, growing from near-nothingness into vast, continent-sized features. This is the essence of inflation. In a span of time so brief it makes a nanosecond seem long, the entire fabric of space itself expanded exponentially, smoothing the overall geometry of the cosmos into the flat universe we measure today. But as it stretched, it also took those fleeting quantum fluctuations and locked them in, magnifying them from subatomic ripples into macroscopic wrinkles in the density of the universe. These frozen ripples became the primordial seeds of all structure. Where a quantum bubble had created a region of slightly higher density, a bit more gravitational pull resided. Where there was a region of slightly lower density, a gravitational valley formed. Inflation stamped these patterns across the entire sky, creating a cosmic blueprint. Without this explosive stretch, those quantum whispers would have remained lost, and the universe would have expanded into a forever dilute, featureless fog of particles, never able to clump into galaxies or stars. Inflation was the crucial, violent first act that took the featureless chaos of the beginning and imprinted it with the subtle, gravitational melody that would eventually orchestrate the birth of everything. This cosmic blueprint was still just a pattern of energy, a ghostly map of what could be. For it to become real, the universe needed its first solid pieces. That transformation began as the firestorm finally started to cool. The relentless expansion of space acted like a cosmic pressure release valve, thinning out the frenzied quark-gluon plasma and allowing its temperature to plummet. Think of a pot of boiling water on your stove. When the heat is intense, the water is a turbulent, chaotic vapor. But as you turn the heat down, that steam begins to condense, coalescing into distinct droplets of liquid. A similar, far more dramatic condensation happened across the entire cosmos within its first microsecond. During that unimaginably hot beginning, the fundamental forces of nature were unified, behaving as a single, symmetrical power. But as the temperature dropped past a critical threshold, something extraordinary happened. The strong nuclear force, the glue that would later bind atomic nuclei together, froze out. It separated from the unified electroweak force in a sudden cosmic phase transition. This was not a gentle change. It was a violent shift, like supercooled water instantly crystallizing into a lattice of ice. The release of pent-up energy from this symmetry breaking sent powerful shockwaves rippling through the still-forming universe. Most importantly, this event changed everything for the quarks and gluons zipping about in the plasma. Before this moment, the energy of their surroundings was so intense that any quarks that briefly linked up were immediately blasted apart. But now, with the strong force acting as a distinct, powerful glue, quarks could finally snap together and stay that way. They bound into permanent trios, forming the first stable protons and neutrons. From a formless, seething ocean of pure energy, the first tangible, persistent pieces of matter had emerged. This was the universe making its first concrete decision, moving from a realm of fleeting possibilities to one containing durable building blocks. These protons and neutrons were the primordial seeds of all atomic nuclei, the essential ingredients for every star, planet, and living thing that would ever exist. In a single, violent microsecond, chaos had taken its first definitive step toward becoming structure, forging the very bedrock of our material reality from the cooling ashes of creation. With the first protons and neutrons now stable, the universe entered its next great act of alchemy. For a brief, spectacular window, the cosmos itself became a titanic nuclear reactor. This period, known as Big Bang Nucleosynthesis, began just a few minutes after the beginning, as the universe continued its frantic expansion and cooled to a temperature of around 1 billion degrees. That might sound unimaginably hot, and it is, but it was finally cool enough for something new to happen. The protons and neutrons, once zipping about independently, could now get close enough for the strong nuclear force to grab hold and bind them together. Imagine a frantic, crowded dance floor where the music is finally slowing down, allowing partners to lock hands and form pairs. The first and simplest fusion product was deuterium, a heavy isotope of hydrogen consisting of one proton and one neutron. But this was just the beginning. These deuterium nuclei were themselves rapidly slammed into other protons and neutrons, building up into the next element on the periodic table, helium. For roughly 17 minutes, this cosmic forge raged, with collisions and fusions happening everywhere. Yet the universe's own expansion was the ultimate timekeeper. As space stretched, the density of particles plummeted and the temperature dropped further. Soon, the particles were too far apart and moving too slowly to overcome their mutual electrical repulsion and fuse. The window for nuclear cooking slammed shut. In that short, critical span, the universe manufactured almost all the helium that would ever exist, along with trace amounts of lithium. Everything else, every single heavier element, would have to wait for another, much later forge. The result was a universe composed of a remarkably simple elemental soup. Mass, it was roughly 75% hydrogen nuclei, the single protons, and 25% helium nuclei, with only the faintest sprinkling of lithium. This was the primordial chemical signature of the cosmos, the direct ash left behind by the Big Bang's fire. For hundreds of millions of years, this would be the only raw material available, a vast, featureless expanse of hydrogen and helium gas, imprinted with the gravitational seeds from inflation, but waiting for a spark. This simple two-ingredient universe held within it the entire future of complexity, for these light elements would become the sole fuel for the first generation of stars, whose violent lives would ultimately forge the carbon, oxygen, iron, and all the other elements of our world. The stage was now chemically set, but the universe remained a dark, structureless sea. How would those subtle gravitational whispers finally pull this gas together to light the very first fires in the cosmic dark after that brilliant flash of nuclear creation? The universe entered a profound and silent chapter. For nearly 200 million years, a cosmic fog settled in. The fierce light of the primordial fire had finally faded, its last photons stretched and cooled by the relentless expansion of space until they shifted into the invisible microwave part of the spectrum. This left the cosmos in a state of near-total darkness. No stars had ignited yet, no galaxies swirled. The universe was a vast, expanding sea of neutral hydrogen and helium gas, utterly black and silent to any hypothetical observer. The only source of illumination was that faded afterglow of creation itself, now so it was undetectable to any form of sight. This epoch is known as the Cosmic Dark Ages, and it was the longest, quietest night in history. But to call it empty would be a profound mistake. This era was one of immense hidden activity. The gravitational seeds from inflation were still there, woven into the fabric of this dark sea. In regions of slightly higher density, the pull of gravity was a tiny bit stronger. Yet this force faced two powerful opponents. First was the outward pressure of the gas itself, a thermal pushback against collapse. Second, and far more dominant, was the overall expansion of space, which constantly tried to pull everything apart, diluting the gas thinner and thinner. For a very long time, expansion and gas pressure won. Gravity was the tortoise in this cosmic race, patient and relentless, but moving with agonizing slowness. So the Dark Ages were not a static pause, but a slow-motion incubation. Picture a perfectly still, dark pond on a windless night. Beneath its glassy surface, however, currents are subtly at work. A leaf drifts into a slight eddy, then another and another. Almost imperceptibly, a small cluster begins to form. This is what gravity was doing across the entire universe. Atom by atom, over millions of years, it tirelessly gathered matter into those slightly denser regions imprinted by the quantum whispers of inflation. The gas began to pool, drawn by its own collective weight. These pools grew denser, and as they did, their gravitational pull became stronger, attracting even more gas from their surroundings. It was a feedback loop of breathtaking patience, a whisper gradually amplifying itself into a shout. This dark, foggy universe was therefore pregnant with potential. Every future galaxy, every cluster of stars, every planet was encoded in those slowly concentrating clouds of hydrogen and helium. The stage was being set in utter darkness for a transformation so dramatic it would rip the cosmic fog apart and flood the universe with light for the very first time. The quiet gathering within the cosmic fog had a single, relentless director. While the forces that govern light and atoms are powerful, their influence is short-ranged, acting only across tiny distances. Only one force possesses the infinite patience and the universal reach to sculpt a cosmos over billions of years: gravity. It is the master architect of the large-scale universe, a whisper that becomes a shout across the vastness of space and time. Think of a gently rolling landscape after a rain. The water does not stay evenly spread across the hills, it naturally trickles downward, gathering in the valleys and the lowest points, forming streams and eventually ponds. In the early universe, the subtle density ripples from inflation created a similar, invisible topography. A region with just a few more particles than its surroundings had a minutely stronger gravitational pull. This made it a shallow well in the fabric of space-time. Over eons, surrounding gas, drifting in the expanding void, would feel that gentle tug and slowly, imperceptibly, begin to slide down into that well. But there was a hidden player in this gravitational drama, one that would build the framework for everything to come: dark matter. This mysterious substance, which does not emit, absorb, or reflect light, felt gravity's pull just like normal matter. Crucially, because it does not interact with the pressure of light or the push of electromagnetic forces, it faced no resistance. While clouds of hydrogen and helium gas were buffeted by the fading heat of the Big Bang, dark matter could simply collapse under its own weight. Long before the first star flickered, dark matter was already condensing into vast, invisible spheres and halos, tracing out the gravitational blueprint of the future cosmos. These dark matter halos became the essential skeletons upon which galaxies would be built. Their immense, unseen gravity provided the deep traction, the powerful wells, needed for the normal gas to finally fall in. The silent, relentless pull of gravity was the universal engine, transforming the faintest random ripples into concentrated hubs of matter, setting the stage for the next, brilliant phase, the dawn of light itself. Deep within the densest knots of that primordial gas, a new threshold was finally crossed. For millions of years, gravity had patiently gathered hydrogen and helium into vast, dark clouds. As these clouds contracted, their cores grew hotter and denser, a slow crescendo of pressure building toward an inevitable climax. When the temperature at the heart of a collapsing cloud soared past 10 million degrees, a new and unstoppable fire was lit. The immense pressure forced hydrogen nuclei, simple protons, so close together that they overcame their natural repulsion and fused, transforming into helium and releasing a torrent of pure energy in the process. Nuclear fusion, the engine of a star, had ignited for the very first time in the history of the cosmos. The cosmic dark ages were over in a flash of light. This was the cosmic dawn. These first stars, known to astronomers as population 3 stars, were unlike anything in our night sky today. Born from the pristine, simple soup of hydrogen and helium, with no heavier elements to help them cool and fragment, they grew to monstrous proportions. They were likely behemoths, hundreds of times more massive than our own sun. Imagine a furnace so vast and intense that it burned a brilliant, searing blue-white, pouring out ultraviolet light with a ferocity that would make our sun seem like a dim ember. Their lives were spectacularly short and violent, measured in mere millions of years instead of billions, burning through their colossal fuel reserves at a frantic pace. Their birth was nothing less than a cosmic revolution. For the first time since the afterglow of the Big Bang faded, a new source of light pierced the universal blackness. This was not the faded, uniform glow of cooled creation, but the focused, energetic glare of a local furnace. This starlight became a new and powerful force in the universe. The intense ultraviolet radiation streaming from these first stars began to bombard the surrounding sea of neutral hydrogen gas that filled intergalactic space. One by one, the ultraviolet photons smashed into hydrogen atoms, stripping away their electrons in a process called. The cosmic fog, which had shrouded the universe for so long, began to clear, becoming a transparent, ionized plasma. The universe was no longer a passive, dark expanse. It was now an active and luminous arena, where starlight could travel freely for the first time, etching its patterns across the cosmos. The age of structure had truly begun, but the violent lives of these first giants would ensure that their legacy was written not just in light, but in the very chemistry of creation. The violent brilliance of those first stars held a secret recipe written in nuclear fire. Inside their searing cores, a cosmic alchemy was, transforming the simple hydrogen and helium of the Big Bang into something entirely new. This process is called stellar nucleosynthesis, and it is the reason our world is made of more than just those two elements. It begins with the same fusion that gives a star its light, hydrogen atoms forced together under immense pressure to create helium. But in the heart of a truly massive star, the story does not end there. As the helium accumulates, the core grows hotter and denser, reaching a new critical threshold. The helium atoms themselves begin to fuse, slamming together to form carbon, the fundamental backbone of all organic chemistry. Then, layer by layer, the star becomes a nested furnace. In a shell around the carbon core, helium fusion continues, while deeper inside, carbon atoms fuse to create oxygen, neon, and magnesium. Further in, oxygen fuses into silicon and sulfur. Each new fusion stage requires higher temperatures and pressures, each step forging a heavier element and releasing a burst of energy that keeps the star from collapsing under its own weight. This layered burning creates a cosmic onion, with iron slowly accumulating at the very center. Iron is a special element, and its formation marks the end of the line for this stellar factory. Fusing iron does not release energy, it consumes it. For millions of years, the star had been a self-sustaining engine, but now, with an iron core growing at its heart, it was building its own doom. The star's final act is one of unimaginable violence. When fusion can no longer support the outer layers, gravity wins in a single catastrophic moment. The core collapses in less than a second, then rebounds in a shockwave of such ferocity that it tears the entire star apart. This is a supernova explosion, a flash that can outshine an entire galaxy. In that fleeting, inconceivable inferno, conditions become so extreme that they forge every element heavier than iron. Neutrons flood the exploding material, slamming into atomic nuclei to build copper, zinc, silver, and gold. The intense heat and pressure create radioactive elements like uranium and plutonium. Then, in a final, magnificent act of cosmic recycling, the supernova blast hurls this newly forged material outward at nearly the speed of light, scattering it across vast stretches of interstellar space. The pristine clouds of hydrogen and helium from the early universe are now polluted, enriched with carbon, oxygen, nitrogen, silicon, and iron, along with traces of every other natural element. This stellar dust is the raw material for everything that comes next: rocky planets like Earth, the water in our oceans, and the complex chemistry that makes life possible. We are literally made of stardust, the recycled remains of those ancient, giant stars that lived fast, died young, and in their spectacular deaths, gifted the cosmos with the ingredients for complexity. That supernova blast wave is far more than a brilliant finale. It becomes a cosmic sculptor, its shockwave racing outward at thousands of kilometers per second, a supersonic wall of energy slamming into the surrounding clouds of cold gas and dust. This impact is not a gentle nudge. It is a titanic compression, like a sudden, powerful gust of wind hitting a field of dandelion seeds. The shockwave violently squeezes the interstellar gas, increasing its density and triggering profound gravitational instabilities. In some regions, the compression is so intense that it overcomes the gas's internal pressure, pushing it past the critical point where gravity can finally take over. A cloud that was once stable and drifting may suddenly fragment, its densest knots collapsing under their own weight to ignite new stars. This process, called triggered star formation, is a breathtaking example of cosmic recycling, where the violent chaos of a star's death directly catalyzes the birth of a new generation. The shockwave carves and molds the interstellar medium, creating intricate structures like the beautiful, glowing nebulae we see through telescopes, which are often both the graves of old stars and the cradles for new ones. But the shockwave's role does not end there. As it expands, it sweeps up the newly forged heavy elements from the exploded star, mixing them thoroughly with the pristine hydrogen and helium of the surrounding cloud. This ensures that the next generation of stars and any planets that form around them will be born from enriched material. They will contain carbon, oxygen, iron, and all the other elements essential for rocky worlds and the chemistry of life. A supernova, therefore, is not merely a destructive end. It is a fundamental agent of change, a recycler on a galactic scale. It takes the simple ashes of the first stars, forges them into complexity, and then scatters those ingredients across space, ensuring that each new stellar cycle begins with a richer, more diverse palette. The galaxy becomes an ecosystem, where death feeds new life, and chaos repeatedly gives birth to ever more intricate forms of order. These swirling stellar nurseries were not destined to drift alone. As the first generations of stars lit up the darkness, a larger, more majestic architecture was emerging. Gravity, the patient architect, was now working on its grandest canvas yet, drawing thousands of these stars together into the first islands in the cosmic sea, the proto-galaxies. Picture not the stately, pinwheel spirals we know today, but smaller, ragged collections of stars, enshrouded in vast cloaks of that pristine hydrogen and helium gas. They were dynamic and chaotic, born within the immense, invisible scaffolding of their dark matter halos. In the crowded early universe, these proto-galaxies were constantly brushing past one another, their gravitational fields tangling in a slow cosmic dance. Often, they would merge, two clouds of stars and gas smashing together in a spectacle that would last hundreds of millions of years. These collisions were not destructive ends, but creative acts. They stirred the galactic pot, funneling gas toward the center and triggering furious bursts of new star formation, building up the mass and structure of the emerging galaxy. Within each of these swirling pools of gas, a simple physical principle was shaping their ultimate form, the conservation of angular momentum. As a giant cloud of gas collapsed under its own gravity, any tiny bit of initial spin became amplified, just as an ice skater spins faster when they pull their arms in. This spin prevented the cloud from collapsing into a simple sphere. Instead, it flattened out into a vast, rotating disk, where most of the gas and new stars would eventually reside. Not all motion was orderly, however. Random, churning motions within the cloud contributed to the formation of a central bulge, a dense, spherical hub of older stars at the galaxy's heart. This combination of structures, a rotating disk and a central bulge, became the classic signature of spiral galaxies like our Milky Way. But a galaxy is far more than just a collection of stars. Its true significance lies in its gravitational depth. A single star's gravity is too weak to hold onto the gas and heavy elements blown out by supernovae. That precious enriched material would simply drift away into the void. A galaxy, however, with the combined gravitational pull of billions of solar masses anchored by its dark matter halo, creates a gravitational well deep enough to act as a cosmic reservoir. It can trap that ejected gas and newly forged metals, holding them within the galactic neighborhood. This changes everything. It means that the products of stellar alchemy are not lost, but recycled locally. Within a galaxy, star formation becomes a self-sustaining cycle. One generation of stars' lives dies and enriches the surrounding gas clouds. Gravity then pulls that enriched gas together to form a new generation of stars, which are now born with a richer supply of heavy elements, making rocky planets more likely. This cycle can continue for billions of years, allowing for the gradual buildup of complexity within a stable, localized environment. The emergence of galaxies marked a fundamental shift in the universe's organization. Stars were no longer isolated beacons, but citizens of vast, gravitationally bound cities. These cities became the engines of chemical evolution, the protected workshops where the simple elements of the Big Bang could be patiently forged into the diversity of a living cosmos. Yet within the swirling heart of these young galactic cities, a new and far more extreme kind of structure was taking shape. From the chaos of countless collisions and mergers, an object of unimaginable density began to form at the very center, a supermassive black hole. These cosmic giants, containing the mass of millions or even billions of suns compressed into a point of infinite density, likely have their origins in those earliest, most violent days. They may have grown from the collapsed cores of the very first, monstrous population 3 stars, or perhaps from the direct, runaway collapse of immense gas clouds in the crowded galactic core. Whatever their precise birth, their presence became a defining force. A supermassive black hole is not a passive pit, it is a dynamic engine. As vast rivers of interstellar gas are drawn in by its immense gravity, the material does not fall straight down. Instead, it spirals inward, forming a flat, whirling structure called an accretion disk. Friction and tidal forces within this disk heat the gas to temperatures of millions of degrees, causing it to glow with a brilliance that can outshine every star in the galaxy combined. This is the power source of a quasar, an active galactic nucleus that turns the black hole from an invisible sink into the most luminous object in the cosmos. The energy released is so colossal it creates powerful jets of charged particles that blast out from the poles at nearly the speed of light, stretching for thousands of light years into intergalactic space. This furious output creates a profound paradox. The most chaotic, destructive objects in the universe become master regulators of galactic order. The intense radiation and searing jets from the quasar can heat the surrounding galactic gas, preventing it from cooling and collapsing to form new stars. In some cases, these winds can even push vast quantities of material completely out of the galaxy, effectively shutting down star formation for a time. This process, called feedback, is now understood to be crucial. Without a central black hole to occasionally put the brakes on, a galaxy might convert all its gas into stars in a single, frantic burst, leaving it a static, aging system. The black hole's violent activity, therefore, helps to pace a galaxy's growth, ensuring a long, sustainable evolution. It is a stunning cosmic balance, a gravitational monster born from chaos, whose very fury helps sculpt the stable, structured galaxy that surrounds it. This grand architecture does not end at the galactic scale. If we could pull back far enough to a vantage point encompassing billions of light years, the true masterpiece of cosmic structure would reveal itself. The universe is not a simple scattering of isolated galaxies. Instead, it forms a vast, three-dimensional tapestry, a delicate filigree of light and matter known as the cosmic web. This is the largest pattern in existence, the ultimate expression of gravity's patient work over nearly 14 billion years. Its design is both elegant and haunting. Dense, glittering clusters of thousands of galaxies sit at the intersections like brilliant, crowded cities. Connecting these clusters are long, faint filaments, threads of galaxies and diffuse gas that stretch across the unimaginable voids. And between these threads lie the voids themselves, enormous, spherical regions of near-total emptiness so vast that a single one could contain thousands of galaxies side by side with room to spare. This cosmic web is not random. It is the direct, grown-up version of those microscopic quantum ripples from the universe's first moment. The subtle hills and valleys in the density of the primordial plasma, stretched to cosmic proportions by inflation, became the blueprint. Over eons, gravity simply followed the map. Matter, both dark and normal, drained out of the low-density valleys, the future voids, and flowed along the ridges, merging into the filaments and finally pooling into the dense clusters at the nodes. In this way, dark matter acts as the invisible skeleton of the entire structure. Its halos define the gravitational pathways along which normal matter, the gas and stars we can see, later assembled. Observing the cosmic web today is an act of profound archaeology. We are looking at a fossilized imprint of the universe's infancy, a snapshot of the quantum whispers from the first trillionth of a second, now written across the sky in galaxies and emptiness. It shows us how the faintest possible imprint of chaos, by cosmic forces, could weave itself into the grandest, most beautiful architecture imaginable. This cosmic web holds within its threads a specific, measurable echo from the universe's fiery youth. To find it, we must listen not with our ears, but with our telescopes, tuning into a faint, fossilized rhythm imprinted on the distribution of galaxies themselves. This echo is known as Baryonic acoustic oscillations, and it is the universe's most enduring sound wave. To understand its origin, we need to return to that early searing plasma before the first atoms ever formed. For hundreds of thousands of years, the universe was not a collection of distinct particles, but a single, tightly coupled fluid. The ordinary matter, protons and neutrons known collectively as baryons, was hopelessly entangled with the intense sea of light, the photons. Where gravity tried to pull the baryons together into denser clumps, the immense pressure of the trapped photons would push back outwards, creating a powerful restoring force. This set up a continuous tug-of-war, a rhythmic push and pull that generated actual sound waves, or pressure waves, rippling outward through the primordial soup at over half the speed of light. Each wave was a spherical shell of compressed matter and radiation, expanding from every single one of those initial density seeds. But this cosmic symphony could not last forever. When the universe cooled enough for stable atoms to form, a profound decoupling occurred. The photons, suddenly freed from their long entanglement with matter, streamed away in every direction, becoming the cosmic microwave background we detect today. At that precise moment, the sound waves stopped in their tracks. They froze, leaving their final imprint as spherical shells of slightly denser matter, now anchored in place. The radius of these shells became a fixed scale in the cosmos, a preferred distance determined by how far a sound wave could travel in that plasma before the music stopped. This distance is colossal, nearly 500 million light-years across. Fast forward to today, and we see the ghost of those waves in the way galaxies are arranged. When astronomers map millions of galaxies, they find a subtle statistical preference. You are slightly more likely to find two galaxies separated by that specific, fossilized sound wave scale than by any other distance. It is as if the universe has a faint, barely perceptible grid, a ruler etched into the fabric of space itself during its first 400,000 years. And this is why baryonic acoustic oscillations are so precious to cosmology. They give us a standard ruler of known physical size. By observing how this ruler appears stretched or compressed at different distances, and thus at different eras in cosmic history, we can measure the expansion rate of the universe with extraordinary precision across billions of years. We are not just seeing structure, we are measuring it with an ancient echo, using the frozen music of creation to understand the very dynamics of space and time. The clearing of that cosmic fog was the final, necessary act to make the universe truly observable. For hundreds of millions of years after the Dark Ages, the vast spaces between the first stars and proto-galaxies were filled with a sea of neutral hydrogen gas. This gas was a relic of the Big Bang, and it acted like a pervasive, faint mist, absorbing the energetic ultraviolet light from the earliest stars before it could travel very far. The universe, though now dotted with brilliant points of light, was still shrouded. This began to change as those first stars and the energetic cores of young galaxies poured out torrents of ultraviolet radiation. When a high-energy photon from a star slammed into a neutral hydrogen atom, it could knock the atom's single electron clean away. This process, called ionization, transformed the atom into a positively charged ion, a free proton and a free electron drifting separately in space. This was the start of, think of it like a vast, frozen lake under a rising sun. At first, only the areas directly beneath the sun's rays begin to melt, forming small pools of liquid water. In the early universe, the first stars and galaxies were those isolated points of heat. Around each one, a growing bubble of ionized, transparent plasma would form, a cavity carved out of the neutral hydrogen fog. As more stars ignited, more bubbles appeared. Over hundreds of millions of years, these bubbles grew larger and began to touch and merge, their boundaries intersecting like soap suds slowly filling a basin. The process was neither instant nor uniform. Some regions of the cosmos were early, while pockets of the stubborn primordial fog persisted in the voids, the emptiest regions farthest from any source of light. Eventually, the bubbles overlapped completely, and the fog lifted for good. The intergalactic medium had a permanent phase change, from a neutral gas to a fully ionized plasma, a state it remains in today. This was the universe's final great transition, a necessary cleansing that allowed light to become a true citizen of the cosmos. Without, the brilliant light from all later galaxies, including our own Milky Way, would have been absorbed and scattered after only a short journey. Our telescopes would see only the faint, blurred glow of the very nearest stars. Cleared the windows, granting light the freedom to travel across billions of light years and carry the stories of distant galaxies directly to us. It marked the moment the universe finally stepped out of its formative shadows and into the luminous, transparent era we inhabit. But gravity was not the only force quietly shaping the newborn cosmos. Across the vast, dark clouds where stars were being born, another invisible hand was at work, one that could not pull matter together but could guide its flow with ghostly precision. This is the story of cosmic magnetic fields, the universe's silent sculptors. In the grand scheme of forces, magnetism is incredibly weak, far weaker than gravity on large scales. Yet its subtle influence is woven into the fabric of nearly every structure we see. The origins of these fields are a profound mystery. They may have been born in the violent turbulence of the early universe itself, as seething plasma created faint, primordial ripples in the electromagnetic fabric of space. Or perhaps they were sparked later, in the chaotic environments around the first stars and galaxies. Wherever they began, these weak seed fields did not stay weak for long. As immense clouds of gas began to collapse under gravity, they often spun, churning the ionized particles within them. This motion, acting like a natural dynamo, could amplify a faint magnetic field tremendously, twisting and stretching it until it became a significant force. Picture a vast, dark cloud of gas beginning to condense. Without a magnetic field, it might collapse into a simple, formless blob. But thread that cloud with invisible magnetic lines, like cosmic fiber optics, and everything changes. The field creates a subtle architecture within the chaos. Charged particles become trapped, spiraling along these lines. The field resists being compressed, adding a gentle pressure that can slow a cloud's collapse, giving it more time to fragment in complex ways. Most importantly, it channels material. Gas does not simply fall inward randomly. It flows preferentially along the magnetic field lines, funneling matter into specific regions. This guided collapse can determine the ultimate size and number of stars that form from a single cloud. On a smaller scale, as a dense core forms a protostar, the magnetic field becomes entangled in the swirling disk of material feeding it. Here, the field performs a crucial sleight of hand. It acts as a brake, helping to transport angular momentum, the energy of spin, outward from the infant star. Without this magnetic braking, the spinning disk would fling material away, preventing the star from growing. Instead, the field allows the star to gather mass while also launching powerful, focused jets of material from its poles, piercing the surrounding cloud like cosmic blowtorches. These jets are a direct signature of magnetic guidance, visible proof of this invisible force at work. On the grand stage of a galaxy, magnetic fields play a longer, quieter game. They are woven through the spiral arms, aligned with the disk, contributing a faint pressure that helps support the galaxy's vast structure against gravitational collapse. They guide cosmic rays, influence the birthplaces of stars within giant molecular clouds, and add a layer of delicate order to the turbulent interstellar medium. So while gravity draws the map, magnetism often draws the roads, providing subtle pathways that direct the flow of matter on its journey from formless gas to shining star. This invisible sculptor works in concert with the crushing force of gravity, adding a final layer of intricate detail to the universe's emerging masterpiece. This hidden framework remains the greatest unsolved puzzle in cosmology. We have mapped its gravitational influence across the cosmos, yet we have never directly seen a single particle of it. This is the enduring mystery of dark matter, the unseen foundation upon which all visible structure is built. Its defining characteristic is its profound silence. Unlike the protons, neutrons, and electrons that make up our world, dark matter does not interact with the electromagnetic force. It does not absorb, reflect, or emit light. It is utterly invisible to our telescopes, passing through normal matter and itself like a ghost. This very aloofness, however, gave it a decisive head start in the race to build the cosmos. While normal matter was buffeted by the intense pressure of radiation in the hot early universe, unable to clump effectively, dark matter felt only gravity. Unimpeded, it could begin collapsing into vast, diffuse halos almost immediately after the Big Bang, tracing out the gravitational skeleton of the future cosmic web long before the first star ever flickered. These invisible wells of gravity became the essential templates. When the universe cooled and normal matter finally decoupled from light, it had a map to follow, flowing into the pre-existing gravitational valleys carved by dark matter. Every galaxy we see now sits nestled within and is shaped by one of these immense, unseen halos. The nature of this mysterious substance is the subject of intense investigation. The leading idea suggests dark matter is cold, meaning its particles move relatively slowly. This slowness allows it to clump efficiently from the smallest scales upward, leading to a universe rich with small satellite galaxies and complex substructure within halos. An alternative theory proposes warm dark matter, where particles move faster, smearing out small-scale clumps. This could explain why we observe fewer small satellite galaxies around our Milky Way than simple cold dark matter simulations predict. The search for a definitive answer involves scrutinizing the faintest, smallest galaxies in the universe and the detailed structure of galactic halos, looking for the subtle fingerprints of dark matter's fundamental properties. Regardless of its exact form, the evidence for its existence is overwhelming and comes from multiple, independent cosmic witnesses. The rotation curves of spiral galaxies show stars on the outer edges moving just as fast as those near the center, defying the laws of gravity unless an immense halo of unseen mass is holding them in orbit. The phenomenon of gravitational lensing, where the gravity of a massive cluster of galaxies bends the light from objects far behind it, reveals that the cluster's true mass is many times greater than the sum of its visible stars and gas. Even the precise patterns in the cosmic microwave background, the baby picture of the universe, require a specific amount of dark matter to explain the sizes of the hot and cold spots we observe. It is the indispensable cosmic glue. Without the deep, anchoring gravity of these dark matter halos, the magnificent structures we cherish would simply fly apart. The whirlpool of a galaxy would unravel, its stars scattering into the void. The great clusters, those cities of galaxies, would dissipate. The beautiful filamentary tapestry of the cosmic web would never have woven itself together. Dark matter provides the stable, massive foundation that allows the normal matter, the stuff of stars, planets, and us, to gather, cool, and ignite into the luminous universe we call home. We are living in a world built upon a shadow, our very existence made possible by an invisible architecture we are only just beginning to comprehend. The universe builds itself in layers, a magnificent hierarchy of structure that ascends from the invisible to the immense. It begins with the most fundamental particles we know, quarks. In the cooling aftermath of the Big Bang, these quarks, bound by the strong nuclear force, formed the first stable protons and neutrons. This was the universe's first act of permanent assembly, creating the durable seeds of all atomic nuclei. Under the right conditions of heat and pressure, these nuclei then captured electrons to become complete atoms, primarily hydrogen and helium. Gravity then took these simple atoms and drew them together across vast, dark spaces. They coalesced into colossal, frigid clouds known as molecular clouds, cosmic nurseries light years across. Within these turbulent clouds, gravity triggered a new phase of fragmentation. Dense knots within the gas collapsed further, their cores heating until nuclear fusion ignited, and a star was born. But stars are social creatures. They rarely form in isolation. The same gravitational pull that created one star will often create thousands or millions more from the same cloud, binding them into a swirling collective, a galaxy. And just as stars gather into galaxies, galaxies themselves are drawn together by their mutual gravity. They form groups, then massive clusters containing hundreds or even thousands of galaxies. These clusters, in turn, align themselves along the great filaments of the cosmic web, the largest structures in existence. This entire ascent, from a single quark to a supercluster of galaxies millions of light-years wide, follows a clear, bottom-up logic. It is a story of hierarchical assembly. Each new level of complexity is built from the stable structures of the level below it, all orchestrated by the relentless, patient force of gravity acting upon those initial quantum seeds. The breathtaking complexity of our cosmos is not a random accident. It is a logical, nested pattern, a cosmic architecture where every star, every galaxy, and every cluster finds its place in an elegant sequence of growth that stretches across nearly every scale of reality. But how can we possibly test this grand narrative of cosmic construction? We cannot rewind the universe and run the experiment again. Instead, we have built a new kind of laboratory, one that exists entirely within the logic of silicon and electricity. This is the realm of supercomputer simulations, our most powerful tool for replaying the cosmic movie. Scientists begin by encoding the known laws of physics, gravity, fluid dynamics, thermodynamics, into vast computational models. They then set the initial conditions, using the precise snapshot of the infant universe captured by the cosmic microwave background as the starting point. Into this digital cosmos, they introduce the mysterious actors we cannot see, parameters for dark matter and dark energy. With everything in place, they press a virtual play button and let the simulation run. Over months of computation, these models, with names like TNG and Millennium, fast forward through nearly 14 billion years of cosmic history. We do not just watch a sped-up film, we witness a dynamic, evolving universe being born from equations. Countless particles, representing dark matter and gas, interact under the programmed laws. We see dark matter condense into its cosmic web, watch gas flow along the filaments, and observe the first proto-galaxies ignite. We witness galactic collisions in slow motion, see supernova shockwaves trigger new star formation, and watch black holes grow at the centers of galaxies, their energetic feedback regulating the growth of their stellar cities. These simulations are more than just spectacular visualizations, they are crucial testing grounds. By tweaking the input physics, perhaps changing how stellar winds are modeled or how black hole feedback operates, and then comparing the resulting virtual universe to the actual one we observe through our telescopes, scientists can determine which processes are truly essential. They help us ask and answer profound questions. Would galaxies look the same without dark matter? How important are galactic mergers in determining a galaxy's shape? The simulation becomes a digital crucible, distilling the chaos of cosmic evolution into understandable cause and effect. It is our closest approximation to a time machine, transforming static telescope images into a living, breathing story of a universe in constant, magnificent flux. Yet, for all the power of our simulations, they remain a theory until they meet the light from the sky. That crucial evidence now arrives from a silent observer stationed 1,000,000 miles from Earth, the James Space Telescope. Its mission is not to see the universe as it is, but as it was, acting as humanity's ultimate time machine. The key to its vision is a simple but profound cosmic fact. As light travels across the expanding universe, its waves are stretched, shifting from visible colors into the infrared part of the spectrum. The farther away an object is, and the further back in time we look, the more extreme this becomes. For the very first galaxies, their visible starlight has been stretched so dramatically over billions of years that it arrives at our doorstep as pure infrared radiation. This is why it was built, with a colossal gold-coated mirror and instruments exquisitely tuned to detect this ancient, cooled glow. It does not see the brilliant blue stars those galaxies once had. It feels the faint, long-wavelength heat signature they left behind. By staring for days at what appeared to be empty patches of sky, collects these whispers, building them into portraits of the infant cosmos. What it has found is both breathtaking and deeply puzzling. It has identified candidate galaxies that existed when the universe was only 300 or 400 million years old, a mere toddler by cosmic standards. These systems are not the faint, wispy proto-galaxies many models predicted. They appear shockingly bright, massive, and already structured. Even more startling, their light shows the chemical fingerprints of heavy elements like oxygen and carbon. This suggests that within just a few hundred million years of the first star's birth, entire generations of stars had already lived, died in supernovae, and enriched their galactic homes. It is as if we expected to find a cosmic nursery and instead discovered a bustling, well-established city. These observations are not breaking our theories of cosmic evolution, but they are stress-testing them, forcing a refinement of the timeline. How did gravity assemble so much material so quickly? Did the first stars form in incredible monolithic bursts, or were the seed structures from the dark matter web far more pronounced than we thought? Deep field images are more than just pretty pictures. They are data-rich puzzles, each pixel a line in the story of how chaos first crystallized. With every new observation, this telescope is bringing the era of first light into sharp focus, allowing us for the first time to compare our grand simulations of cosmic dawn against the actual, ancient light that witnessed it. This magnificent age of structure, however, is not the universe's final state. We currently live within a fleeting, vibrant chapter, a temporary oasis of light and complexity bookended by two vastly different kinds of emptiness. The force that will ultimately close this chapter is the same one that first revealed its existence through observations of distant supernovae, dark energy. Unlike gravity, which pulls things together, dark energy is a property of space itself that causes it to expand at an accelerating rate. Think of the universe not as a static stage, but as the fabric of a stretching balloon. For billions of years, gravity fought this expansion, pulling galaxies into clusters and weaving the cosmic web. But around 5 billion years ago, the balance of power shifted. As the universe grew larger and more dilute, dark energy's repulsive push became dominant. The stretching of space itself began to accelerate. In the near cosmic future, this acceleration will have profound and isolating consequences. First, it will sever the connections between the great structures we see today. The galaxies within a bound cluster, like our own local group, will remain gravitationally tied, eventually merging into single, giant elliptical galaxies. But the space between these isolated supergalaxies and the other great clusters of the cosmic web will stretch at an ever-increasing pace. Over tens of billions of years, the light from any galaxy outside our own merged supercluster will be stretched so far that it shifts into undetectable radio waves, and then its wavelength will become longer than the observable universe itself. Each island of stars will be surrounded by an impenetrable horizon of darkness, its night sky going completely, forever black. The universe will have pulled its great cities apart, leaving them in solitary, silent confinement. Within these isolated galaxies, the story turns inward and grows dimmer. The era of star formation is finite. Galaxies are not closed systems. They are constantly using up their reservoir of cold gas, the raw material for new stars. As existing stars die, they recycle some of their material, but much of it gets locked away in stellar remnants or blown out into intergalactic space by supernovae. With dark energy accelerating the expansion, that ejected gas is lost forever, unable to fall back into the galaxy to fuel a new generation. One by one, across the cosmos, galaxies will exhaust their gas. The last stars will ignite, and after tens of billions of years more, the last stars will burn out. What remains will be a cosmic graveyard of fading embers. The universe will be populated by the cold, dark remnants of stellar evolution, white dwarfs that slowly cool to black, neutron stars, and the supermassive black holes at the galactic centers. Even these formidable objects are not eternal. Through a process predicted by Stephen Hawking, black holes are thought to slowly lose mass by radiating energy, a trickle of particles escaping their immense gravity. For a stellar mass black hole, this Hawking radiation is so faint that its evaporation would take timescales longer than the current age of the universe. But given enough time, an almost inconceivable amount of time, even the largest black holes will eventually evaporate in a final, faint puff of radiation. This leads to the possible final state, a universe governed by thermodynamics. All energy gradients will have evened out, all structures dissolved. It may become a cold, dark, and profoundly dilute sea of fundamental particles and radiation, spread so thinly that no further work can be done, no new structures can form. This is a state physicists call maximum entropy, or the heat death of the universe. It is a haunting, poetic symmetry. The cosmos may end in a kind of stillness that echoes its beginning, not a searing, dense fire, but a frozen, vast emptiness. Both states are equally featureless, equally devoid of the complex structures we cherish. This immense timeline frames our present reality with startling clarity. The age of galaxies, the era of shining stars and swirling nebulae, is not the default state of the cosmos. It is a brilliant, temporary flowering, a vibrant phase of dynamic change nestled between two extremes of simplicity. We are living in the cosmic springtime, witnessing the universe at its most creative and alive. The grandeur of our structured universe leads to a startling and deeply personal question. Why does this cosmos seem so perfectly arranged for beings like us to exist within it? The fundamental numbers that govern reality appear to be fine-tuned with almost impossible precision. If the force of gravity were just a fraction stronger, the universe would have collapsed back on itself almost immediately after the Big Bang, snuffing out any possibility of expansion and growth. If it were a fraction weaker, matter would never have clumped together, leaving the cosmos a forever thin, dark haze without a single star. The density of those primordial quantum ripples was also critical. Slightly larger fluctuations, and matter would have clumped into enormous black holes before stars could form. Slightly smaller, and galaxies might never have coalesced at all. Even the mysterious cosmological constant, which drives the accelerating expansion of dark energy, is balanced on a razor's edge. A value much larger, and the universe would have torn itself apart before life could arise. A value much smaller, and gravity would have recollapsed everything long ago. This delicate balance of constants and conditions seems less like a random accident and more like a lock with a very specific combination, one that happens to open the door to complexity, chemistry, and conscious observers. This observation leads us to the anthropic principle, a simple but profound idea. It states that we can only observe a universe that is compatible with our existence as observers. In a cosmos where the constants were not aligned to allow for stars, planets, and stable chemistry, there would be no one around to wonder about them. The universe appears fine-tuned for life because we are here to see it. One compelling explanation for this apparent fine-tuning is the concept of a multiverse. Imagine not one universe, but a vast, perhaps infinite, ensemble of universes, each with its own random set of physical laws and constants. In most of these cosmic bubbles, the numbers would not line up. They might flash into existence and vanish, or expand into eternal, barren emptiness. But in a vanishingly small fraction of them, by sheer statistical chance, the constants would fall into the narrow golden zone that permits structure and life. We, inevitably, find ourselves in one of those rare, habitable universes. Our cosmic home is not special because it was designed, but because it is the only kind of universe we could ever call home. This perspective reframes our existence from a central mystery to a statistical inevitability within a much grander, stranger reality. Yet for some, this multiverse explanation feels like a cosmic shrug, pushing the ultimate question of why one step further back. It invites a deeper reflection on the nature of reality itself. Is the existence of a multiverse, with its endless variety, a more fundamental law? Or could there be a single, elegant theory that logically requires the constants to have the values we observe, making a life-friendly universe not a lucky accident but a necessary outcome? We do not yet have the answers. What the fine-tuning of our universe truly highlights is the profound interconnection between the largest scales of cosmology and our own intimate existence. The quantum whispers of the first moment, the strength of gravity, the push of dark energy, these are not abstract concepts in a distant realm. They are the very reasons you have a world to stand on and a star to warm you. They are the prerequisites for every story ever told, every question ever asked. Whether through a fortunate roll of the dice in a multiverse or a deeper principle we have yet to uncover, our structured, luminous, living universe stands as a testament to a reality where chaos, against all odds, found a way to become us. This ancient yearning to explain our origins is written in the stars of human imagination. Long before telescopes or particle accelerators, our ancestors looked at the world around them and asked the very same question cosmology grapples with today. How did all this magnificent complexity arise from apparent nothingness? Their answers took the form of powerful creation myths, stories that resonate with an uncanny similarity to the scientific narrative we've just traced. Across countless cultures, the starting point is nearly always the same, a primordial, undifferentiated state. The ancient Greeks spoke of chaos, a yawning, formless void that existed before the gods. From this emptiness, the earth goddess Gaia and the sky god Uranus emerged, establishing the first structures of the world. In the Babylonian, the universe begins as a swirling, tumultuous sea of salt water, as the goddess Tiamat. The story describes how order is carved from her chaotic body to form the heavens and the earth. Similar themes echo in the Norse myth of a great void flanked by realms of fire and ice, whose mingling sparks the first life. These are not mere fantasies. They are profound philosophical attempts to address the ultimate mystery. They represent the human mind observing a structured reality, the regular cycle of seasons, the dependable rising of the sun, the intricate patterns of life, and instinctively reaching back for a beginning that must have been its opposite: disorder, void, or chaos. The core narrative arc is identical: a featureless starting condition, a catalyst or a creative act, the emergence of fundamental separations, like sky from earth or light from dark, and finally, the slow building of the complex world we know. This pattern reveals a deep, intuitive understanding that the universe we inhabit is not a default state, but an achievement. It is the product of a great transformation. Our modern scientific story, from the quantum foam to the cosmic web, is the latest chapter in this timeless human endeavor. It is our culture's creation myth, meticulously built not from oral tradition, but from the painstaking language of mathematics and the evidence of observation. It replaces gods with fundamental forces, and a chaotic sea with a quark-gluon plasma, yet it answers the same awe-filled question. Recognizing this connection does not diminish the scientific account, it elevates it. It places our quest for cosmic understanding within a grand, shared human tradition, a continuous, multi-thousand-year conversation about where we came from and how the magnificent tapestry of existence was first woven. We are still telling the same story, only now we are beginning to read it in the original script written across the sky itself. The story of cosmic structure is not a distant fable. It is the biography of the very atoms that make you who you are. Those heavier elements, the essential ingredients for life itself, have a single, exclusive origin. Carbon, the backbone of every organic molecule. Nitrogen, a key component of our DNA. Oxygen, which fills our lungs with every breath. Phosphorus, which helps store energy in our cells. Not one of these was present in the primordial fire of the Big Bang. Each was forged much later, deep within the heart of a star, under pressures and temperatures we can scarcely comprehend. They were created in that layered stellar alchemy, and then scattered across the galaxy by the very supernovae that ended those stars' lives. This fact transforms our understanding of our place in the cosmos. Every single atom in your body, with the sole exception of the hydrogen, which dates back to the first few minutes of creation, was once part of something else. It was forged in a stellar furnace and then hurled across space by a cataclysmic explosion. The calcium that strengthens your bones was once part of the dying breath of a red giant star. The iron that carries oxygen in your blood was fused in the final seconds before a supernova. The oxygen you are breathing right now was created in a star that shone billions of years before our sun even ignited. We are, in the most literal and physical sense, made of stardust. This is not a metaphor. It is a chemical fact, written into the very composition of our bodies. We are collections of atoms that have journeyed across the galaxy and through time, recycled through generations of stars, to eventually come together here and now. This means we are far more than passive inhabitants of a vast universe. We are the universe itself, temporarily arranged into a form complex enough to look back and wonder. We are a structure born from chaos, a pattern of stardust that has, for a fleeting moment, become conscious. Our ability to tell this story, to trace our lineage back to the first quantum whispers and the first stellar explosions, is perhaps the most profound outcome of that entire 13.8 billion-year journey. From dust to stars and back to dust made aware, the story of cosmic structure does not end with galaxies and stars. It continues on a smaller, more intimate scale, within the swirling cradles of dust and gas that orbit newborn suns. For our own solar system, this was a local story, a private act of creation. But we now know it is a universal one. Across the galaxy, wherever a star ignites, the same fundamental processes begin to sculpt new worlds from chaos. This is the era of exoplanets, and it reveals that the universe's drive to build intricate order is even more prolific than we ever dreamed. When a young star first shines, it is often surrounded by a vast, flattened disk of leftover material, a disk. Picture the vibrant rings of Saturn, but on a scale millions of times larger, a spinning platter of gas and microscopic dust grains that stretches for billions of miles. Within this turbulent disk, the same physics that built galaxies begins anew on a miniature stage. The force is gravity, but the first steps are almost impossibly delicate. Tiny motes of dust, finer than smoke, drift through the nebula. When they gently collide, electrostatic forces can make them stick together like cosmic dust bunnies. This is the first act of planetary assembly, moving from microscopic grains to pebbles, then to larger rocks. As these clumps grow, their gravitational pull becomes stronger. They begin to sweep up more material from their orbital path, growing from rocks into mountain-sized planetesimals. In a dramatic and chaotic period, these planetesimals collide and merge in a series of colossal impacts, forming embryonic worlds called protoplanets. The inner disk, hot from the young star's fury, favors the formation of rocky, metallic worlds. Farther out, where temperatures plummet, volatile ices can solidify, allowing gas giants to rapidly accumulate vast atmospheres of hydrogen and helium. Over millions of years, the disk clears, blown away by stellar winds or accreted onto the growing planets, leaving behind a newborn solar system, a fresh island of complex structure orbiting its star. For most of human history, this was just a theory based on our own solar system. Then, in the mid-1990s, everything changed. Astronomers began detecting the first planets orbiting other stars, not by seeing them directly, but by observing the subtle wobble they induced in their host star's motion. Since then, with missions like TESS, we have confirmed thousands of exoplanets, and the numbers suggest there are billions more in our galaxy alone. We have found a staggering diversity of worlds, hot Jupiters orbiting blisteringly close to their stars, super-Earths larger than our home but smaller than Neptune, and planets orbiting binary stars, much like the fictional. Most significantly, we have identified numerous rocky planets orbiting within their star's habitable zone, that temperate region where liquid water could pool on a world's surface. This profound discovery means the universe's tendency to create structured, complex systems is not a rare fluke. It is a standard, almost inevitable outcome of star formation. Wherever a star is born, the physics of gravity, angular momentum, and collision will often conspire to build a planetary system. The cosmic drive that assembled galaxies from quantum ripples and stars from interstellar clouds also builds planets from stardust. This suggests that the basic ingredients for a world like Earth, rocky material, liquid water, organic chemistry, are likely scattered abundantly across the Milky Way. We are not a singular masterpiece, but one beautiful example of a universal pattern. The chaos of a collapsing cloud reliably gives rise not just to a star, but to a whole new archipelago of ordered worlds, each a fresh canvas where the next great transition, from chemistry to biology, might one day begin. Yet even as we map this grand, predictable architecture, a profound truth emerges about our own specific place within it. The universe builds its large-scale structures with a kind of inevitable clockwork logic, but the creation of a single star, a single planet, or a single living world is a story written in chance. This is where the insights of chaos theory enter the cosmic stage, particularly the famous idea known as the butterfly effect. In simple terms, it describes how tiny, nearly imperceptible differences in a starting condition can lead to wildly different outcomes over time. A butterfly flapping its wings on one continent might, through a long chain of atmospheric events, influence the formation of a storm weeks later on another. This sensitivity to initial conditions is not just a feature of Earth's weather, it is woven into the fabric of cosmic evolution itself. On the grandest scales, the story is remarkably deterministic. Given the exact pattern of those initial quantum ripples and the known laws of physics, a powerful computer simulation can predict the overall cosmic web, the distribution of galaxy clusters and vast voids, with stunning accuracy. The large-scale blueprint was set in stone within that first fraction of a second. But zoom in on a single galaxy, and especially on the process of star and planet formation within it, and the narrative shifts from destiny to a delicate dance of probability. Here, the outcome for any particular system becomes exquisitely sensitive to a cascade of tiny, random events. Consider the birth of our own solar system some 4.6 billion years ago. It began within a giant molecular cloud, a fragile structure itself shaped by the gravitational tides of the Milky Way and the shockwaves from long-dead stars. A slight asymmetry in that cloud's rotation, a passing star that gravitationally nudged it, or a shockwave from a relatively nearby supernova could have meant the difference between our sun forming or not. That supernova shockwave might have been the very trigger that caused our local pocket of gas to collapse, but if it had arrived a million years earlier or later, or from a slightly different angle, everything would be different. Even after the sun ignited, the chaotic ballet continued. The disk was a crowded, violent construction zone. Planetesimals, the building blocks of planets, collided and merged in a game of gravitational pinball. A single slightly different collision angle between two of these embryonic worlds could have sent Earth into a wildly different orbit, or prevented its formation entirely, leaving behind only a scattered belt of asteroids. The specific arrangement of planets in our system, their sizes, their compositions, and their orbits, are not the only possible outcome from the same starting materials. They are the unique result of one specific sequence of countless chaotic interactions. This duality defines our cosmic story. The universe was destined to build galaxies, stars, and planets in abundance. That much was written into the quantum code at the beginning. But the existence of this particular planet, orbiting this particular star, with this precise mix of elements and conditions that allowed life to arise, was not guaranteed. It is the product of a long, fragile chain of cosmic coincidences, a single thread woven through a tapestry of near-infinite possibilities. Our home is both a statistical inevitability and a breathtakingly rare accident, a world born from the beautiful, chaotic interplay between the universe's grand design and its countless tiny, unpredictable whispers. This galactic history is not locked away in some distant archive, but written in the very stars above us. To read it, astronomers have become cosmic archaeologists, sifting through the stellar population of our own Milky Way as if it were a vast fossil bed. Each star is a time capsule, preserving within its light the precise chemical conditions of the cloud from which it was born. The oldest stars, found primarily in the halo and globular clusters that surround the galactic disk, are remarkably metal-poor. Their atmospheres contain only trace amounts of elements heavier than hydrogen and helium, telling us they formed from gas that had been touched by very few, if any, prior supernovae. They are the pristine relics of the galaxy's infancy, forged when the universe itself was young and chemically simple. In stark contrast, younger stars like our Sun, located in the galactic disk, are metal-rich. They contain a significant abundance of carbon, oxygen, iron, and silicon, elements that could only have been manufactured inside earlier generations of stars and scattered by their explosive deaths. This stellar chemistry is a direct lineage. A star's metallicity acts as a birth certificate, telling us not just when it formed, but from what kind of material. By analyzing this chemical fingerprint across millions of stars, we can reconstruct a timeline of enrichment, watching as the galactic gas supply was gradually polluted with the ashes of successive stellar generations. But the story is told not just by chemistry, but by motion. The European Space Agency's Gaia mission has been performing a monumental census, precisely mapping the positions, distances, and velocities of over 1 billion stars in our galaxy. This data lets us rewind their orbits, tracing their paths backward through time to see where they came from. What emerges is a history of violent growth and peaceful accretion. The smooth, orderly rotation of the thin disk stars speaks of a relatively quiet, settled period of star formation from a well-mixed, enriched gas disk. The chaotic, randomly oriented orbits of the older halo stars, however, tell a different tale. They are the survivors of ancient galactic building blocks, small proto-galaxies that were shredded and absorbed by the growing Milky Way billions of years ago. Some of these stellar streams, like the faint river of stars known as Gaia Enceladus, are still visible today, ghostly remnants of a dwarf galaxy that merged with our own in the distant past. By combining chemical clues with dynamical maps, we can assemble a biography of our galaxy. We see it beginning as a collection of chaotic, collapsing clouds, growing through dramatic mergers that stirred the stellar population and triggered furious bursts of star formation, before finally settling into its current, more tranquil spiral structure. The Milky Way is not a static sculpture, but a living history book, its every star a page recording a specific chapter of construction, from the first pristine sparks to the latest, complex worlds born from well-recycled dust. Our understanding of the cosmos has long been built on a single sense sight. We have gathered every story from the faintest glimmer of ancient starlight. But light, for all its brilliance, has its limits. It can be absorbed, scattered, or obscured by cosmic dust. It tells us only part of the story. Now we have learned to listen, to feel, and to sense the universe in entirely new ways. This is the age of astronomy, where we perceive the structured cosmos through multiple channels, each carrying a unique kind of information from the depths of space and time. The first of these new messengers arrives as a ghostly whisper from the heart of stars themselves, the neutrino. Born in the nuclear furnaces that power stars and in the cataclysmic collapses of supernovae, these nearly massless particles barely interact with anything. Trillions of them pass through your body every second, completely unnoticed. This aloofness is their great strength. While a photon of light can take hundreds of thousands of years to struggle out from the dense core of a star, a neutrino escapes almost instantly, carrying a direct, unaltered report from the site of its creation. Detecting them requires extraordinary instruments, like the super detector in Japan, a vast tank of ultra-pure water buried deep underground, waiting for the rare flash when a neutrino finally interacts. By studying solar neutrinos, we confirm the nuclear processes burning at the sun's core. And when a star explodes in a nearby galaxy, a burst of neutrinos arrives hours before the light does, offering the first alert of a stellar death and a pristine view into the engine of the explosion itself. Then, there is the sense of touch, but on the fabric of reality itself. In 2015, a century after predicted their existence, we felt the universe ripple. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the faintest stretching and squeezing of spacetime caused by the collision of two black holes over 1 billion light-years away. These are gravitational waves. They are not made of light or matter, but are literal waves in the geometry of the cosmos, generated by the most violent motions of immense mass. Where light shows us the surface of an event, gravitational waves let us hear the event itself. The merger of two black holes is completely dark, emitting no light at all, but it sings a powerful gravitational chirp as the objects spiral together and collide. The merger of two neutron stars, detected in 2017, produced both gravitational waves and a flash of light across the electromagnetic spectrum, an event that confirmed these collisions as the cosmic forges for heavy elements like gold and platinum. With gravitational wave astronomy, we are no longer just watching the cosmic dance, we are feeling the vibrations of the stage. Finally, there are the cosmic rays, high-energy atomic nuclei, protons and heavier elements that streak across the galaxy at nearly the speed of light. Their origins are among the universe's most powerful natural accelerators, likely supernova remnants, active galactic nuclei, or other extreme environments. When these particles smash into Earth's atmosphere, they create cascades of secondary particles we can detect. They are not messengers in a directed sense, but more like cosmic shrapnel, clues to the immense energies at work in structuring the interstellar medium. By tracing their paths and energies back through magnetic fields, we try to pinpoint the monstrous engines that launched them on their journey. Each messenger reveals a different facet of cosmic structure. Light shows us the beautiful form of a galaxy. Neutrinos tell us about the hidden fusion within its stars. Gravitational waves reveal the invisible choreography of massive objects orbiting one another in the dark. Cosmic rays hint at the turbulent, energetic weather between the stars. Together, they provide a complete sensory picture of the universe. It is the difference between watching a silent film of a thunderstorm and being able to hear the thunder, feel the wind, and smell the rain. We are no longer merely astronomers. We have become listeners, feelers, and participants in a richer, more dynamic, and deeply structured cosmic conversation. This realization that we can read the universe through multiple senses carries a profound philosophical weight. For nearly all of human history, the night sky was considered a permanent backdrop, an eternal and unchanging stage upon which the brief drama of life played out. The stars were fixed in their celestial spheres, and the cosmos was seen as static, infinite, and cyclical. This view offered a certain comfort, a sense of existing within a timeless order. Then, in the 20th century, that eternal stage began to move. This observation that galaxies are racing away from one another revealed an expanding universe. The discovery of the cosmic microwave background, that faded afterglow, confirmed it. We do not live in an eternal, steady-state cosmos. We live in a universe with a definitive beginning, a narrative with a starting point we call the Big Bang. This single scientific fact reshapes our entire philosophical understanding of reality. It means the cosmos has a finite history, a story that is still being told. All the magnificent structure we see, from the great galactic filaments to the delicate chemistry of a living cell, is not a permanent feature. It is a recent development in an epoch that is 13.8 billion years long. We are not living in the first chapter or even the middle. We have arrived in the latest pages. Think of the entire timeline of the universe compressed into a single calendar year, with the Big Bang at the stroke of midnight on January 1st. In this cosmic year, our Milky Way galaxy forms around March. Our solar system condenses from stardust in early September. Life on Earth emerges by late September. The dinosaurs reign in late December and go extinct on the morning of December 30th. All of recorded human history, every empire, every discovery, every individual life, unfolds in the final seconds before midnight on December 31st. This perspective is simultaneously humbling and awe-inspiring. It instills a deep humility, for we are cosmic newborns, arriving at the very end of an almost unimaginably long chain of events. Our entire species is a fleeting whisper in the vast chronology of creation, yet this same timeline fills our existence with profound meaning. We are not accidental visitors in an ancient, indifferent void. We are the products of that entire story. The quantum seeds, the first stars, the exploding supernovae, the merging galaxies, the formation of our planet, every single step across those billions of years was a necessary link in the chain that led to a universe complex enough to become aware of itself. We are the cosmos, grown up and looking back at its own infancy. This finite history means that complexity, life, and consciousness are not default settings of reality. They are hard-won achievements, the results of a specific and contingent sequence of transformations from chaos to order. Our ability to ponder this journey, to trace our lineage back to the first instant, is perhaps the most remarkable structure the universe has yet built. It invites us to consider our role not as passive inhabitants, but as active participants in this ongoing story, tasked with understanding the chapter we find ourselves in and wondering what might be written next. The grand narrative of cosmic construction is a masterpiece of modern science, yet its most critical chapters remain unwritten. For every elegant answer we have uncovered, a deeper, more fundamental mystery waits in the shadows, reminding us that our understanding is a map that still has vast, unexplored territories. At the very heart of our story lies the profound enigma of dark matter. We have mapped its gravitational influence with exquisite precision, tracing the invisible skeleton of the cosmos. But we have never directly seen a single particle of it. What is it made of? Is it a sea of yet undiscovered subatomic particles, or could it be something even stranger, like primordial black holes formed in the universe's first chaotic moments? Every experiment designed to catch a whisper of dark matter, from detectors buried deep in mines to particle colliders, has so far returned only silence. This silence is not a failure, but a clue, telling us the answer may lie in physics beyond our current imagination. Equally mysterious is dark energy, the force accelerating the expansion of the universe. Is it a constant property of empty space itself, as once proposed, or is it a dynamic field that has changed over cosmic time? Its true nature will determine the ultimate fate of all structure, whether the cosmic web will stretch into eternal, isolated threads, or if some other, unknown destiny awaits. Then there is the pivotal moment that set everything in motion: cosmic inflation. We see its fingerprints in the smoothness of the universe and the pattern of the cosmic microwave background. But what triggered that explosive burst of expansion in the first trillionth of a second? What was the engine, and what, if anything, existed before that moment? Our laws of physics break down at such extremes, pointing toward a theory of quantum gravity that remains just out of reach. Even the story of the first structures is filled with puzzling gaps. The James Space Telescope has shown us galaxies that grew massive and complex shockingly early. How did gravity assemble them so quickly? Did the first stars form in unimaginably dense bursts, or is our understanding of dark matter's role in those first moments incomplete? And how did supermassive black holes, weighing billions of suns, come to exist in the cores of young galaxies when there seemed to be no time for them to grow? These are not minor details. They are gaping holes in the plot of our cosmic history. Perhaps the most subtle mystery of all is one of balance. In the earliest particle collisions, matter and antimatter should have been created in equal amounts, destined to annihilate each other into pure radiation. Yet here we are, in a universe made almost entirely of matter. Somewhere, a fundamental asymmetry, a tiny violation of symmetry in the laws of physics, tipped the scales. Without that 1 in a billion imbalance, no atoms, no stars, no galaxies, and certainly no us would have ever formed. Finding the source of that cosmic bias is a quest that spans from the largest telescopes to the most sensitive underground labs. These unanswered questions are not failures of science, they are its very lifeblood. They are the driving force behind the next generation of cosmic explorers. The Sea Observatory will scan the entire sky every few nights, watching for the subtle effects of dark energy on the growth of structure. The Nancy Grace Roman Space Telescope will hunt for primordial galaxies and the faintest signatures of exoplanets. Giant neutrino observatories and ever more sensitive gravitational wave detectors are coming online, promising to listen to the universe in ways we never could before. Each new instrument is a question posed to the cosmos, and we eagerly await its reply. The story of how chaos became structure is not a closed book sitting on a shelf. It is a living document, its pages constantly being edited, revised, and expanded with every new observation and every bold theoretical leap. Our current narrative is the best model we have, a stunningly successful framework that explains so much of what we see. But these lingering mysteries are a beautiful reminder that the universe is always more subtle, more strange, and more wondrous than our latest chapter can describe. They invite us to keep looking up, and to keep wondering, knowing that the next great discovery might rewrite everything we think we know. This epic transformation from void to vibrancy is not a random accident. It is the story of a universe whose fundamental laws contain a beautiful, inherent bias toward building complexity. The simple, elegant rules of gravity, quantum mechanics, and nuclear physics act as a cosmic recipe, and when given enough time and the raw ingredients of energy and space, they inevitably bake galaxies, stars, and planets. We have followed the trail of evidence from the frozen whisper of the cosmic microwave background to the violent nurseries of distant nebulae, and it all points to a cosmos that is creative by its very nature. Those first quantum ripples were not flaws in a perfect emptiness, they were the essential first strokes on a blank canvas, the necessary imperfections from which all beauty could grow. This means the night sky is more than a scattering of distant suns. It is a living genealogy. Every spiral galaxy is a descendant of a dark matter seed. Every star is a great-grandchild of the first stellar giants. Every planet, including our own, is a testament to the recycling power of supernovae. And we, sitting here on this pale blue dot, are the universe's most recent and perhaps most astonishing creation. We are matter that has become conscious, stardust that has learned to look up and trace its own family tree back to the very beginning. This connection is not metaphorical. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged in the heart of a star that lived and died long before our sun was born. You are a walking, talking archive of cosmic history. So when you step outside on a clear night and gaze upward, you are not a separate observer looking at a foreign scene. You are the universe looking back at itself. You are a part of that grand structure observing the rest of its family. Each pinpoint of light is a chapter in an autobiography 13.8 billion years in the telling, and you are living the latest page. If this journey from the formless fire to the structured cosmos has reshaped how you see your place in it, consider subscribing for more explorations into the universe's deepest mysteries. And we would love to hear from you. Share in the comments which moment in this story, from quantum whispers to galactic cities, amazed